Question 1. Water contaminated with mercury contains methyl mercury ions. These ions are absorbed by living organisms, then slowly metabolized and excreted. Young fish were taken at regular intervals from mercury contaminated lake and tested to determine mercury ion content. And we have been given the graph where time is on x-axis and mercury ions on y-axis. Question A1. Mercury ion concentration follows a linear trend. Linear trend during first 5 months. Deduce the equation for this part of the graph. So you can see is a linear trend, and we can use equation of straight line, which is y is equal to mx plus c, where y is the concentration of mercury ions, x is a time, and m is gradient. So gradient will be equal to delta y over delta x. And if we read from the graph day 5, and we can see the mercury ion concentration is 0.010, time is 5. So if I solve this, that will give me 0.0020. So it means the mercury ion concentration will be equal to, so Hg plus ion concentration will be equal to 0.0020 times by time. So x is time. So this is the equation for this part of the graph. 2. Suggest why the mercury ion concentration changed very little after 8 months. We can see is plateau there, it stays the same, and we can say that then the rate of uptake is equal to rate of metabolism or excretion. 3. State why methyl mercury ion is more likely to be absorbed by the fish than mercury. It means methyl mercury is more soluble in water, so CH3Hg plus is more soluble in water than Hg. So the reason can be, if we draw CH3Hg plus, which is ion, and water has dipoles, so we have lone pairs there. This is partial negative, this is partial positive, so there'll be an interaction between positive ions and dipole. So that interaction is called ion dipole interaction. Hence, it makes methyl mercury to be more soluble in water than mercury. B. The concentration of mercury ion in sample of the fish is 0.0052 plus minus 0.0001 microgram mercury per gram. Calculate the mass of mercury in microgram in 3.723 gram of sample. So if we multiply 3.723 gram with concentration 0.0052, it has a units of microgram mercury per gram. So gram will cancel with gram, and our answer will be in microgram. So if I solve this, that will give me 0.019 microgram. Calculate the percentage uncertainty of methyl mercury ion. So percentage uncertainty is equal to absolute uncertainty, which is given 0.001, and the concentration is 0.0052 times by 100. So if I solve this, that will give me almost 2%. C. Suggest two variables which should be controlled when sampling the muscle tissues. Range of answers are possible, so we need to write down two of them. We can say type of fish, we can say depth or area where the fish is captured, depth or area where captured. You can say part of or tissue of fish, part or tissue of fish, or we can say water content of the muscle tissue, we can say tissue of fish, temperature. Question 2. Pure copper oxide is heated in the presence of hydrogen. Copper oxide is reduced to metallic copper. The formula of oxide can then be determined. We have been given a setup in this figure, and we have a reduction tube, and we pass hydrogen through the reduction tube. A. Suggests why it is important that hydrogen gas flows continuously from before heating begins until the product has cooled. So the reason why before heating, so we might have oxygen or air inside the reduction tube. So to displace air or oxygen from the reduction tube. So if we don't remove, what will happen? So we need to provide the reason. So the reason why, to avoid combustion, so hydrogen will react with oxygen, so there will be a combustion reaction. So avoid combustion, or we can say explosion, because hydrogen is very flammable gas. So explosion of hydrogen. Until product has cooled. So why we need the flow of hydrogen? So to prevent reoxidation of, to prevent oxidation of copper back to copper oxide. B. State two measurements needed to determine the empirical formula of the oxide. So we need mass of copper oxide at the start. So mass of copper oxide before heating, and so mass of reduction tube after heating. In other words, that will be mass of copper after reduction. Outline how the mass of oxygen can be determined. So we can subtract mass of copper from mass of copper oxide we started with, and that way we can have the mass of oxygen. Suggest why amount of oxygen per mole of copper is often less than expected, and how the error could be minimized. So the reason can be incomplete reduction, so there's still some oxygen left, incomplete reduction, or we can say copper reoxidized, we can say heat for long time to minimize the error, so making sure all oxygen is removed. Or we can say use a higher temperature, to make sure all the oxygen has left, or increase the surface area so making sure all oxygen has removed. Question 3. Pasteurization is used to eliminate pathogenic bacteria. The concentration of vitamin C was monitored over a period of time in pasteurized and unpasteurized orange juice. We have been given a graph where on x-axis we have storage time and on y-axis we have concentration of vitamin C microgram per centimeter cube. Identify the dependent variable. So dependent variable is a variable we're trying to determine, and normally dependent variable is plotted on y-axis and independent variable is plotted on x-axis. So in this question, concentration of vitamin C is a dependent variable. So writing concentration of vitamin C will give us a mark. 2. Calculate the decrease in concentration of vitamin C in microgram per centimeter cube caused by pasteurization. So let's go back and read from the graph. So on 0 day, unpasteurized orange juice, it was 410, 20, 30, so 430 microgram per centimeter cube. And on 0 day, pasteurized orange juice, it looks like is around 242 to 243. So if we read 243, so 430 minus 243, so 430 minus 243, and that will give us 187 microgram per centimeter cube. 3. Calculate the average rate of decrease of vitamin C concentration for the pasteurized juice in microgram per centimeter cube per day for first 56 days. So for pasteurized, average decrease, so what was at the start and what was the end? So we started with 243, is ending around 203 or 4, so 203. So change in concentration divided by time. So we will have, we started with 243 and finish with 203. So the change is 40, and 40 divided by 56 will give us the rate. And if I solve this, that will give me 0.71 microgram per centimeter cube per day. 4. Deduce, referring to the graph, whether pasteurization affects the rate of change of vitamin C concentration during storage of orange juice. So if we go back and look in the graph, and change for pasteurized was 40, 243 to 203, and change for unpasteurized, so 432 we have almost 390. So the change for unpasteurized is 430 to 390. So that change is 40 as well. So the change here was 40 as well. So we can write no, because both lose 40 micro centimeter cube in 56 days. 5. The absolute uncertainty in each vitamin C concentration measurement was plus minus 2 microgram per centimeter cube. Deduce with a reason whether the concentration of vitamin C in pasteurized or unpasteurized orange juice has a larger uncertainty, percentage uncertainty. Percentage uncertainty is equal to absolute uncertainty divided by measured value times by 100. So for pasteurized, absolute uncertainty, so plus minus 2 divided by measured value was 243 times by 100. So the percentage uncertainty will be equal to, if we calculate this, 0.82%. And for unpasteurized, it will be plus minus 2 divided by 430 times by 100, and that will be 0.47%. So we can write it will be lower for unpasteurized, and it will be larger for pasteurized. So larger for pasteurized, and the reason why we are dividing with lower concentration or smaller number, lower concentration or smaller number or value. B. UV treatment is an alternative to pasteurization that minimizes the loss of nutritional components. Deduce the type of electromagnetic radiation absorbed in the absorption spectrum of vitamin C. Use section 5 of the new data booklet. So section 5 in old data booklet was section 3, in new IB data booklet is section 5. So if we look in the data booklet, 400 to 700 nanometer is visible region, because the maximum absorbance here is around here, so from 250 around 280 or 290, and this region falls in UV region, so UV ultraviolet region of electromagnetic spectrum. So we can write down UV ultraviolet or ultraviolet. 2. Deduce giving a reason the color of vitamin C. As we can see, there is no absorbance in the visible region 400 to 700 nanometer. So there's no absorbance in visible region, hence the color will be, so it will be white, and does not absorb in visible 400 to 700 nanometer region. 3. Suggests why the use of UV light is not effective for the elimination of pathogenic bacteria in orange juice. Well, the UV light didn't penetrate, didn't reach to pathogenic bacteria, so we can write down does not reach pathogens as UV light is absorbed by other chemicals. 4. Identify 2 ways to decrease the rate of change of vitamin C concentration due to oxidation during the storage of brand juice. We can store at low temperature and we can put in a sealed container or seal under vacuum or store in absence of air or oxygen. The concentration of vitamin C and pH of different fruits were measured. So we can see as the concentration of vitamin C milligram per dm cube increases, the pH decreases. So 5.07 to 4.25. So there's a negative relationship. Deduce with the reason whether the data shows a correlation between the concentration of vitamin C and pH. So yes, we can say yes, there is a negative correlation between concentration of vitamin C and pH. Or we can work out R square value, which is called correlation coefficient. Using calculator, and if we work out, that will come as a minus 0.7. So there's a negative correlation. The concentration of vitamin C ascorbic acid can be measured by performing a redox titration using acidified iodate and iodide ions. Starch react with excess iodine once the vitamin C is consumed to produce a dark blue black complex. Reaction 1, iodate plus iodide plus acid, they react together, give us iodine. So in the first step, iodine is liberated, is produced, and in reaction 2, ascorbic acid react with iodine. 1. Identify the oxidizing agent in reaction 1. So oxidizing agent is a species that gains electron and itself gets reduced and oxidizes others. So if we look in reaction 1, IO3 minus is changed into I2, so oxidation state of iodine on product side is 0, and oxidation state of iodine, so minus 2 times 3, so iodine will be plus 5. So plus 5 to 0 is reduction, and we can say iodate IO3 minus aqueous is oxidizing agent, as IO3 minus reduced to I2 by gaining electron. hence acting as an oxidizing agent. 2. The student recorded the end point, then noticed the blue color in the conical flask disappeared, suggests why this occurred. So the equivalence point hasn't arrived yet. So all ascorbic acid hasn't reacted yet. So we can write vitamin C was still present. So vitamin C was still present, hence equivalence point was not reached. So vitamin C was still present, equivalence point was not reached yet, it reacts slowly, and hence the blue color in the conical flask disappeared. C. State the effect the recorded endpoint has on the value of calculated concentration of vitamin C. If the endpoint was recorded too early, if the endpoint was too early, the calculated value, the calculated concentration of vitamin C will be lower. Suggests why this method cannot be used to measure the concentration of vitamin C in blueberry juice. So the complex of starch with iodine is the same color as blueberry. So we can write down starch iodine complex. Starch iodine complex. Same color as blueberry. So it masks the color change. So endpoint difficult to detect. Question 4. Hydrogen peroxide decomposes to form water and oxygen. The reaction is catalyzed by solid manganese 4 oxide, MnO2 solid. A student carried out a series of experiments to determine how the rate of decomposition depends on the mass of catalyst. Each time a different mass of MnO2 was added to 25 centimeter cube of hydrogen peroxide solution, the oxygen collected in a graduated gas range and volume recorded at regular intervals. So the figure 1 shows time against the volume of gas produced when different masses of MnO2 were added. A. The 0.3 gram data seems to be anomalous, suggests a possible cause for this. So as we can see, with 0.3 gram, less volume of oxygen is collected. So that seems like there is a leak in the system, so gas get escaped. So we can write down a leak of gas from the system. Okay. B. The student hypothesized, based on underlying theory, that doubling the mass of MnO2 would double the rate of catalyzed reaction. C. The result from figure 1 was processed to produce a graph showing how the initial rate weighed with the mass of catalyst. So we have figure 2 in which we have initial rate and mass of MnO2. So as the mass increases, initial rate of reaction increases. Suggests why it is important to have hypothesis on outcome of experiment. It should be possible to test a scientific prediction by experiment, so we can test our scientific predictions. So it should be possible to test a scientific prediction by an experiment. 2. Explain how the student's hypothesis might be supported by the collision theory. So there are factors that affect the rate of reaction. In this case, we are adding solid MnO2, so we need to keep thinking about the surface area. So we can write down doubling the mass. So doubling mass will double the surface area. If surface area doubles, that means double the collision rate. Or we can say frequency of collision doubles. Three, identify the critical control variable that is not specified in the description of method. So one of the very important control variable is the concentration of hydrogen peroxide, which is not mentioned. So the same concentration of hydrogen peroxide should be used. Concentration of H2O2. And another important control variable which is not mentioned is the temperature. So reaction should be carried at the same temperature. C. Outline how the y-axis value in figure 2 are obtained from the result of figure 1. So let's go back and have a look in the figure 2. So on y-axis we have initial rate of reaction, while in figure 1 we have time against the volume of gas produced. So we can get initial rate of reaction from figure 1 by drawing the tangent when time is equal to 0. So tangent drawn to curve at t is equal to 0, and then to find the gradient, which is delta y over delta x. C. Suggest giving a reason whether a best line for figure 2 should pass through the origin. Decomposition of hydrogen peroxide is endothermic reaction. This reaction hardly proceeds under normal conditions, so we can say yes. If we say yes, rate is negligible. Rate is negligible when no catalyst is present. Or we can say yes, rate is 0 when no catalyst present.